Welcome to the class today. Today we will do imperfection in solid due to impurity. So imperfection due to impurity present in the crystal or substance. So the main thing is the application of this is that insulators which are a poor conductor or bad conductor of electricity, they can be converted into semiconductor, and when we have the crystal of the pure substances which are having insulation behavior, they are poor conductor of electricity. When their crystal is induced with some impurities, then from their bad conduction behavior, they are turned into some good conductor behavior, but they are not becoming that good as the metals are, but they are able to conduct electricity, and that is yours, you can say, behavior of a semiconductor. So this is done in two ways, that is, two types of semiconductors are formed due to this impurity. The first is your N type, if N is for negative, and the second is P type, P is for positive. So in this first I will take up the N type semiconductor. N type semiconductor. In this case, if I take example of silicon, which is a poor conductor of electricity, when in the crystal of this, say like if I draw for you the crystal, these are the particles of silicons at their particular site, and these are the bonds through which these atoms are attached. That is your, this is, you can see, non-metal, and therefore this bond will be not ionic, but this bond will be covalent in nature. You know very well, the covalent bond is formed by the sharing of electrons and is a common feature of non-metallic atoms. And silicon is an example of non-metal, not very much pure non-metallic, but still it is a non-metal. So we have silicon atom present everywhere. Here silicon, this is silicon is belonging to the 14th group. I hope you know, 14th group of the periodic table. So silicon is bonded with another silicon, one silicon atom is bonded with another silicon atom by sharing of electrons, and thus a covalent bond is formed. So when this is here, a silicon is mixed, this crystal is mixed with some impurities of this is belonging to group 14, and to this if we add an element of group 15, generally this arsenic or phosphorus, which are belonging to group 15, that is considered. So if I add some particles of arsenic here, so say this silicon is replaced by arsenic, and you take up here this silicon is also replaced by arsenic, and here this silicon is replaced by arsenic, and here again this is replaced by arsenic, and here it is arsenic. Even if you don't take so much, then also, so here I have shown, so here I just put this is, now look here. So silicon has got 4 electrons in the outermost shell which are available for bonding, you know very well. And in group 15 we have 5 electrons in the valence shell available for the bonding. So all this, you can see here, all these 4 electrons of silicon are used. So here also it is used, and arsenic which is having 5 electrons, so every arsenic will be left over with 1 electron which will not take part in bonding because it has 5 valence electron, and neighbor silicons, they have only 4 valence electron. So 1 electron on each arsenic atom will be left unbonded, and that is called free electron. So when this crystal is brought in contact of electrical field, then electrons, this is electric field, they will be entering. If this end you are attached, so electrons will start flowing. This is free electron. Rest electrons of silicon are bonded, they are not free. So this electron will be pushing this one, this will be migrating, this will take this place, this will be moving out from here, will be pushing this will be pushing this, and even here that way also it can go. This is pushing this, and then this, and then this can go out. So this is what you can see here. Electron is flowing because of this free electron, and that is which is present on arsenic. So when elements of group 15 are mixed in the element of group 14 in its crystal, then you can see 1 extra electron is there. So this mixing of the element of group 15 in the element of group 14 crystal, that is called doping. So doping is done, and then what happened? Then this which silicon, when it would have been pure silicon, then it is like insulator, will not be able to conduct electricity because it has no free electron. But when it is doped with arsenic, it has got some free electron, and so it has turned from insulator to the semiconductor. Since extra electron is there on the water, your atom which is introduced, so therefore negative charge is increased, and therefore it is called N-type semiconductor. Now we will see P-type semiconductor. So P-type semiconductor, that is positive. In this case, your example, if take silicon which is of group 14, that is mixed with the element of group 13. Group 13, say gallium. So in that case, what will happen? You can see 1, 2, these are the particles of silicon. These are the particles of silicon, just like your N-type. I don't make many layers. Just see, since you have understood already that these silicon atoms are bonded with one another through covalent bond. The valence electrons are engaged, and so these are all silicon. Silicon, silicon, silicon. So this silicon atom, as you know, has got 4 valence electrons, and all the 4 electrons are engaged. So it has 4 electrons which are in the valence shell, and group 13 they have 3 electrons. So when group 14 element crystal is doped with the elements of group 13, and say here we have one gallium, and here we have one gallium, and here we have got one gallium. So here gallium will be having 3 electrons in the outermost, and they have 4. So this one will be either this or that, whichever. If this is bonded with all the 4, then this will not be getting, this will be bonded, this is bonded, this is bonded, but this will not be, because this has only 3 electrons. So it will be establishing only 3. And so what will happen? Silicon will have one extra electron which will be in the neighbor of this. Similarly here, this is gallium. If this is bonded here, then this electron will be extra. And if this is bonded this side, this is here, then this silicon may have an extra electron. So if this crystal is kept, which is insulator, kept in the electrical field, electrons will move, and because of the movement of this free electron, that will be what this insulator will be turned into semiconductor. So this is p type. In p type, so remember the number, that is group, which group elements are doping which group. So this is here. Now I'll teach you the property of this solids, that is electrical property, that is they conduct electricity. So solids, in terms of, if I talk electrical conductivity, are classified as conductors which freely allow passage of current, which are examples are metals. And here we have the second kind, this is first kind, second kind, that is semiconductors. And examples you can take which are intermediate between metals and non-metals. So you can take as gallium and all. And the third is your insulator, insulators. So here insulators, they won't allow passage of current at all. So you know, plastic, wood and all, and some non-metals like iodine and all, if you take graphite and all, so they are not insulator, they are conductors. But other non-metals, they are poor conductors, and so they are. But the best example of insulator is your wood, plastic, rubber and etc. So here they are not conducting current at all, and they are conducting in the best way, and this is intermediate of the two. So they are not as good as conductor, but not as bad as a insulator. So their conductivity order is ranging 10 to the power minus 12 per ohm per centimeter, per ohm per centimeter, and this is 10 to the power minus 5 to 10 to the power minus 6 per ohm per centimeter, and here they are 10 to the power minus 8 per ohm per centimeter. So this is their conductivity order. Now I'll teach you how these conductors or semiconductors or insulator, they play their role in conductivity, or how the current is flowing through them. They are good conductor or semi or insulator. Why they are able to conduct freely, like in conductors, metals, why they are not able to conduct so freely as in semiconductor, and why they are not able to conduct current at all, that is in insulator. So that one theory is mentioned in your syllabus, that is band theory. So band theory I will explain to you. This is totally based on molecular orbital theory. This molecular orbital theory you have done in class 11th in detail, and so I will take example of lithium. So when lithium molecule is formed, so we will have lithium atom bonded with lithium atom. So how this lithium will be bonded with lithium, that you see. So first I will write the configuration. 1s2 lithium is having atomic number 3, 1s2 and 2s1. So this is according to valence bond theory, the configuration. Another atom of lithium will have this configuration. Both of them are having same. So you have studied when atoms unite together, they form molecule according to molecular orbital theory. I am not going to take that theory in detail because you have already covered in 11th. So when atomic orbitals unite together or this orbital and this orbital, they unite together, they will be forming molecular orbital. And so the molecule which will be formed, that is Li2, will be having 6 electrons. And how will write configuration? I hope you remember. That is, molecular orbital will have two types of orbital. One will be bonding molecular orbital, the other will be non-bonding orbital. So in this first shell we will have bonding 1s2 electron and anti-bonding 1s2. If you don't remember, revise molecular orbital theory from class 11. So this is bonding orbital, this is non-bonding. Bonding orbitals are, molecular orbitals are more stable because energy is low, and here they are not so stable because energy is higher than them. So first electron fell in bonding level, then they go to anti-bonding. So 2 and 2, 4 electrons. So one shell is over. Then we come to this next, sigma 2s, that is bonding, sigma bonding 2s and sigma anti-bonding 2s. We have only 2 electrons, so both of them will come to the lower energy zone, that is bonding 2s orbital, and this is non-bonding having no electron. There may be your 2p orbitals, px and py, you know, but here's bonding 2pz if you remember, and then we have pi 2px is equal to pi 2p y, both bonding, and then will be your anti-bonding and all, but they all are empty, so the order will be followed, that configuration you have done. So if I draw this energy, this water configuration I have, if I draw that to show you the energy diagram, that also you have done. So see here, that is your lithium atom. Lithium we have got, I write for you the configuration 1s2 and 2s1. So first, for first shell I write, this is your 1s which is having 2 electron, 1 atom. So this is lithium, 1 atom. And here you have got lithium, another atom, that is your 1s, lithium atom. Now they will be forming molecular orbital, bonding and anti-bonding. Anti-bonding, you know, is having higher energy, is shown up, and bonding is having lower energy, is shown down. So here we have got, this is your, if I write configuration, lithium which I wrote earlier, and this is lithium molecule. So sigma 1s2, sigma anti-bonding 1s2. So here sigma 1s, and this is 2, here sigma anti-bonding 1s2, both are having. So this part which we have, Okay, this part, this part where electrons are lying. This is here, this part. This is called band. So this is 1s band of lithium, or maybe of any atom. 1s band, and this is fully filled. Electrons are lying into this. Now still we have got one more. If I draw up, then we have 2s, and here we have this is 2s, only one electron, lithium atom still, and here we have 2s, lithium 1, and we have got this. So here we have sigma bonding 2s, and this is sigma anti-bonding 2s. Both are having one electron. So this is another band. So this is next band here, and this is your 2s band, and this is partially filled. Partially filled, not completely filled. So whether band is partially filled or fully filled, that you can know on the basis of the configuration. I'll show you this 2s further in detail in lithium. If I draw again, that is, we have 2s, we have 2px, we move this side, we have 2s, 2px, 2py, 2pz, 2s, 2px, 2py, 2pz. This is lithium atom. If I take, this is having one, but they are having no electrons. If this side I come, I have 2s, 2px, 2py and 2pz. 2s, 2px, 2py, 2pz, this is lithium, another atom. So when the orbital will be formed, we will have molecular orbital. Here we will have sigma anti-bonding 2s, and here we will have sigma bonding 2s. Here one electron, rest are empty. So in this case, both of these electrons will be filled here. Both of these electrons will be filled here. You know that very well, first in the lower energy zone and then in the higher. So this is filled, so anti-bonding is your empty. So only this is, so if this is your band, this region is band where electron lies, so it is only half filled. This part is filled, that is vacant. So, and if I take 2px, you know, bonding will be down, and 2px anti-bonding will be up. So like this, 2py, that is 2p, you know that I am not drawing that. So here we will have sigma 2pz, and here we will have a next 2px, 2py, this is all you have done, and up also. So here, if I show you in short, that is, if lithium atom, which is having, this is your lithium molecule, here lithium atom, and this is lithium molecule. So here one atom, this is your 1s, paired and paired, so this is fully filled. So this is your 1s molecular, this is 1s band in which your sigma bonding, 1s electron and sigma anti-bonding are lying. The next is above this, if I show, that is 2s, one electron, 2s, 1 electron. This is also lithium, this is lithium molecule. So both of them will be here. So if they are here, it means this is half filled and half is vacant. Okay, then above this we have a P and or PX, PY, PZ. So PX, PY, PZ actually they are of the second only shell if I show you. So what is there? They overlap. They are so close that they can even overlap. So if I show like this, if this is your or if I don't show this, this is a 2s. If this is bonding 2s and this is anti-bonding 2s, so both electrons are here, but I don't try this thing, I just show that 2s is overlapping. So 2p which will be overlapping, so here anti-bonding and here it will be bonding. So this portion is overlapping, this is here and this is here. So this portion is being overlapped. If I consider the bond, so this is between P, that is this is your 2s. So it is found that when more orbitals are there, many atoms are there, then many orbitals will be there. So some of the orbitals will even overlap in the metals. So now what is important you have to learn? The orbital which is filled. So here, this is all filled up. So this is the case we see in the metals. In case of metals we have got filled and unfilled, and above this we have got totally vacant 2p. 2p which is vacant. Okay, so this is also there. So this is all vacant, this is partly filled and this is vacant. So two conditions are there in metals. What it will be there? One is this, that is fully filled and then half filled band, this is band. 1s band and this is 2s band. 1s band is fully filled, 2s band is half filled. Either this condition we will have or we can have this condition, that is this is the band which is fully filled and this is the band which is partly filled. I show this way, partly filled. So this may overlap. It is partly filled but it may overlap. So here it is and then here you will have the vacant p orbital. Here we have vacant p orbital. Now just listen carefully. The gap between this gap, the gap between fully filled and this now here, this gap is called forbidden gap. This gap is called forbidden gap. And so here what it will be, just see, in metals what do we have? This empty, this is band, which the band of the orbital which has no electron. Then we have the band of the orbital which is partly filled. Then we have the band of the orbital which is fully filled. So we have these conditions. Okay. So this is one condition in conductor, and what is another condition? This is empty band, and here this is here I showed overlapped. This is here, this is overlapped. So this is partly filled. This is all partly filled. These conditions we have. So this region is your forbidden gap. Forbidden gap. Forbidden gap. Now another term you see. The band which is half filled. Okay, that is, or you can say the last filled band, the last filled orbital. This is the last filled. This is first filled, this is second filled in the last, but not fully filled, half filled. So whether fully filled or half filled, last valence band is this is the last your orbital which is partially filled or fully filled, which is constituting the band. So this band will be called valence band. Valence band. And this is which is empty here. This part which is empty, this is called conduction band. So conduction band is totally empty. Valence band may be fully filled or may be partly filled. So in metals we have both conditions. Either this is fully filled, or if it is fully filled it will be overlapping, and if it is your partly filled it will not be overlapping, but we will be having a gap between conduction band and the valence band. So in this case here it is for metals. In in semi-metals, what is there if I show to you? In semi-metals, this is our conduction band, this is our valence band. I draw three diagrams. So this is valence band, this is valence band, this is valence band. This is fully filled. Okay. This is conductor. This is semiconductor, and this is insulator. So this is your conduction band. This is conduction band. This is conduction band. So first your band, first molecular orbital, that first band which is empty, that is called conduction band, and the last valence orbital which is either fully filled or partially filled, that is called valence band, and this gap is called forbidden gap. So forbidden gap here in semiconductor it is less than 3 eV electron volt. This gap is less than this, and here this gap is more than 3 eV. So and here it is much less than 3.0 eV. So this gap is, if this I take, this gap is A, this gap is B, this is C. So A is least and this is, so this is very wide, so big this gap is. So what happens now? There I teach you how the conduction will be taking place through these bands. So just now see here, in case of here we have these bands, conduction band, valence band, and this is fully filled band. Valence band like this. Now from here valence electrons are there. So they, if it is metal, less than 3 electron volt, less than much less than 3 electron volt. If this gap is there, then when it is heated or when a current is passed, electrons will be excited. They can jump from here, from the valence band to the conduction band very easily, and they will keep on jumping and moving to the other conduction band which are also empty, vacant, and so it will be passing on. So this way current will be conducting. And in semiconductors, this is your less than 3, in that case also they can jump very easily. But in insulator, this is greater than 3.0 electron volt. This is very wide gap. So valence electron on excitement cannot jump from valence bond to the conduction band, and so they will not be able to conduct the electricity. But when insulators are doped, Okay, when insulators are doped, means that impurity is added. So suppose here this is your semiconductor and it is doped with any, just now I explained to you, group 15 and group 13 they can dope. So if impurity is there, what will happen? If here from this valence band, one electron on heating, because this gap is less than 3, so can jump from here to there. So that when it will be jumping from here to there, electron here it will be leaving a hole. Electrons, so other places electrons will be there, but here there will be the hole, means having no electron there. So what will happen? Electron from the lower region, which is close to it, that will be what happened. They will be jumping from here to this, passing it on and filling this gap. So when this will be filled, then a hole will be created here. Okay, and this is filled. Then from here it will be jumping there. So in that case, what will happen? That is your hole is moving down. It was created here when it is got filled from here to there. So hole is created here. So hole is moving down. Okay, and the electron is moving up in the opposite direction. This is another thing you have to remember. The hole created in the valence band that moves down away from the conduction band, and electrons they move in conduction band away from the valence band, and so this way conduction is taking place in the semiconductors. Now here another thing you just listen, that is, if it is a semiconductor by nature, not by impurity, it is a semiconductor, but if you are doping it, if it is a semiconductor and you are, it is able to conduct electricity, then it is called intrinsic type. Of its own, this is the nature. But if you are adding into this an impurity and its conductivity order increases, then it will be by doping, then it will be called extrinsic conductor. So remember two types of semiconductor, intrinsic and extrinsic. Intrinsic, when of their own, without any impurity, they are conducting, correct? Extrinsic, when they are, their conductivity is enhanced because of the addition of impurity, that is called extrinsic conductor. Now, I will teach you the magnetic property. The magnetic properties, two you have to do, magnetic property, and that magnetic property you have done. What is that magnetic property? That is diamagnetic substances are of two types, diamagnetic and paramagnetic. This you have done in detail in coordination compound also I have taught you. Diamagnetic means when all electrons are paired, and paramagnetic when one or many electrons are unpaired. So since electrons are paired, then net dipole moment is 0, and therefore what will happen? They are not attracted by the magnetic field, but slightly weakly they are repelled by the magnetic field, and here they are attracted by the magnetic field because they have one odd electron and they have a paired electron. So this is all about magnetic property you have to do. Electrical conductivity, which I explained to you, the band theory, in a very simple way I explained, but because you have not to do so much in detail in the reduced syllabus, and therefore I have not taught to you in detail that what are the limitations and how electrons will not be able to move beyond the limitations and all, or how the band is formed when many atoms are present in a solid. So this is all about solid state. The solid state is over, and along with this I am attaching that is your PDF file. In that you will find assignment based on solid state. So we'll start next chapter from the next class. Okay, till then, bye.